Good morning, everyone. IEEE PS Student Branch Chapter at IISc and PGCUAE is pleased to invite you to the talk on securing the grid edge, AI-driven cybersecurity solutions for DERMS and critical infrastructure, given by Dr. Prakash Ranganathan. I am pleased to introduce our speaker. Dr. Prakash Ranganathan is the Director of Center for Cybersecurity Research, a National Security Agency designated Center of Academic Excellence in Research. He's also an associate professor in the School of Electrical Engineering and Computer Science at the College of Engineering and Mines, University of North Dakota. His research focuses on AI-driven cybersecurity solutions for critical infrastructure, particularly the electric grid, with emphasis on DER anomaly detection, edge AI, and cyber physical system resilience. He currently leads multiple projects supported by the US DOE CESAR program in collaboration with Argonne National Laboratory and industry partners. Dr. Ranganathan has published over 150 plus peer-reviewed articles, holds two patents, trained 9 postdocs, several graduate students, and has secured more than 15 million external funding from agencies, including NSF, DOD, DOE, FAA, and NASA. He's a senior member of IEEE and brings over 20 years of experience in mentoring research teams and organizing national cybersecurity events. His work integrates machine learning, power systems, and AI-based grid inspection to advance smart, secure, and sustainable infrastructure. He also serves as the site director for NSF Industry University Cooperative Research Center for infrastructure security in the era of AI. We are pleased to have you, sir. Camera needs to be on. Okay. So
okay, that's fine. I think. Okay, anyway, thank you for the microphone. So it's recording, right?
You may have to speak from there only because the mic may not.
Okay, so you want me to stand back here? Can you hear me?
Yes.
First of all, thank you, IISc and Center for Power Grid Excellence in Cybersecurity here, and Dr. Madhu Vindava, Dr. Gurunath, and Dr. Satraj. And appreciate for doing this warm welcome, inviting me here to talk. And like I said, I'm here to share some projects that I've been doing with distributed energy resource management systems. And before I get started, maybe I'll just spend just a couple of minutes on giving some background about my center. I think you can see my.
Keep the mic on this color instead of the other color. I think it works. Yes, sir. It can be put on the middle. Is this one?
The speaker.
No USB. So USB is not there. Yeah. It's okay.
Anyway, UND is a Carnegie Arwin Research Institution, which means that it's one of those highly research activities. The designation is given to those schools in the US for top 100 schools or so, who has strong publications in PhD research and grants. And so we moved to Carnegie Arwin classification last year. And we are also a designated NSA center for cybersecurity. Only a handful of schools has this designation. So before I jump into the talk, I just want to give you a brief overview of my center. We have about 5 full-time research engineers. We have several faculty part of this affiliation to the center who are in AI and cybersecurity, and of course, a number of research fellows and students who are working on this area. Part of our role is also to see, research, also teaching, also to dissemination of outreach of cybersecurity skills. How can we make sure that we build a workforce development and try to get this cybersecurity related careers to in the field, the community. Before I get started, we're doing an IEEE cybersecurity symposium in October. And I invite, its deadline is August 30th. We have industry track, we have, it's virtual, it's hybrid conference as well. So I think I encourage you to submit papers. There is a special session on power system and power grid applications. This may be a good avenue for us to you to submit papers, and for Indian authors, not marketing this, but Indian authors, I'm willing to reduce the fee, even waive the fees if it's actually passes the peer review process. So we need high quality papers. So make use of the opportunity and try to see if you can be able to submit papers here. Okay, and it's October 27 to 30, and it's a 3-day conference, and also we are doing a big capture the flag national competition. I say national, it's also open for everybody. It's a CTF competition. We partner with Meta CTF, and last year we had nearly 60 schools across the country participated. Carnegie Mellon won the first prize, $1,000 first prize, $700 second prize. So if IISc can form a team of 3 or 4 students and wants to participate and capture the flag event, and this is another way for you to get to know the challenges in cybersecurity problems, and that you can compete and get your work recognized. So I'm also promoting this work that it's a way to you to get involved. Let's move on to the presentations of outline. First, I want to talk about what is this DERMS, what is the definition of this, and some architectures. And then I shed some light in threat scenarios, what we actually see in DER networks, and some architectural patterns and zero trust concepts, and some of the work what we have done in autoencoder use cases for power systems. And we have an edge testbed at UND, so we have done some work on federated learning. I have a couple of projects funded on this area, so I will shed some light on this. And of course, some false data injection work what we did, some regression work. I do a lot of forecasting work, so I want to share something on what we've done in hybrid machine learning models, and some collaboration efforts, what this in IUCRC thing is. My first portion of the talk is going to be, giving you a summary of the recent work, what we published in IEEE Communication Service and Tutorials. It is actually a 40, 50-page document, on talking about DER vulnerabilities or DERMS vulnerabilities. The impact factor for 0 is 46.7. It took 2 years to publish this after many rejections and going back and forth. It's a very guiding document that we partnered with a number of individuals, including India, from NIT Trichy and also from NIT Raipur and across the world. So if you really want to get to know about DERMS technology, cybersecurity vulnerabilities, this is a starting point for you to spend some time in reading through. So, DER penetration is increasing every day. You could see that number of solar panels, wind turbines are increasing. And there's a statistics that talks about here that the market share is actually for DER is continuing to grow by 2034, about 1,176 billions. And then you can see that from right now we are at 2025, about 300 gigawatts. It's going to go to 500 gigawatts. Some study even talks about 700 gigawatts. So the growth is real. The demand is real. And which when you have more and more DER participation, there's going to be more and more bi-directional data flow between DER to whatever the system that manages. The system that is managing is so-called DERMS, so it's controlling all these DERs. And either through cloud or software solutions or a dedicated cloud or dedicated network. It's also expected to have a compound annual growth of nearly 18%, on the software solution. So the problem is real. So we need to be aware of what are these challenges that this DERMS technology is going to offer. DERMS is typically used for a wide variety of things. It's for voltage regulation, frequency regulations, a lot of forecasting and energy scheduling, demand response, capacity market, all of these things. Right. Oftentimes there is not an agreement between, what is DERMS to utility, what is DERMS to asset owners, what is DERMS means to users. There is a conflicting definitions of this DERMS, depending on who you speak to. And I'll talk to you about that later, because there is also ADMS and also does a similar work and some of those overlapping functionalities what ADMS is doing. So, so the threat surfaces are increasing, and specifically, we can see that from a solar PV thing, you can see that there's a lot of attacks happening. The number of vulnerabilities and attacks happening in the solar PV area is also compounding to 300% and 220% increases. So you can see the combination of gateways, inverter, applications, cloud, and firewall. So it is happening, and it's real, And I also want to acknowledge Dr. Jayabharat Reddy for being here with me all the way flying from Trichy to here. Thank you for, he's a great collaborator, working on part of the author also for the DERMS review paper as well. And it's very important to understand before we jump into all about DERMS, who are the stakeholders, in this thing. So you could see that you have the market stakeholders, utility stakeholders, aggregators, facilities, and DERs. Going to the lowest level, looking at this yellow color in terms of DER system, where you can have all those assets, DER purpose is to have to generate whatever, renewable sources that you have. It's all connected. Maintenance systems, they may lock out some DER systems, in the event of outages or some kind of a disturbance, or they have to maintain visibility of awareness to see which DERs are active. And you also have distribution system operations, which is also key, in terms of first level one is actually the lower level of your system. And then you have facilities, the load operations, microgrids, those are coming in the level 2 area. And the manufacturers, who are those, so many of OEMs, so many vendors out there, and so there's so many players in terms of in these DER vendors. And you need to understand what their tools look like, what their software look like, what their systems look like, that if you want to interconnect this into the grid. And then you have aggregators, third-party aggregators or in-house aggregators, whether virtual power plants or, the aggregation is all about, you have all these heterogeneous DER sources trying to connect and trying to do this aggregation at minute level or, or every 5-minute level, every 10-minute level to really to see what are these aggregation look like to do the flexible services. So, and then you have at the top, you have these ISOs, RTO, TSO, and then regulators. Regulators are the key ones. They're the one deciding the prices, and you need to be aware of those price signals and mindful about that and see whether how this who can participate in this process of interactions. So this is a very important diagram. You can see it's a very complex arrow going in all directions, and but if you look at IEEE 1547.3 standard, this diagram is pulled from that particular standard document. It gives you a big picture of the same thing in a different way. So you will see the same level 1 has all those DER systems, ranging from the controller, wind, PV, fossil fuel, charging stations, and the lower level devices. Okay? There are standalone devices, the field devices, and they have a process. And then level 2, you can see the blue ones, building management systems. Well, they have their own energy management system. So one may assume that's also a term. So if you talk to different people, they know we already have energy management systems, and so building systems, charging stations, facilities, and then we have something talks about some. So there is more a collections of smaller group of renewable sources that activate the plant. And level 3, if you go third parties, demand response, ADMS. Level 4, DSOs. We have outage management systems. We have GIS. We have all these interconnections, communication capabilities. There's IEEE 2030.5, which is it's also a very important interface that you need to make sure that the interface is actually communicating to other levels. And then you have level 4 ISO and level 5 as the mark. Okay. So all of these are key. And when we did this work, we actually mapped these levels into much more easy to understand figure. At the same time, bringing those standards. So we have this IEEE 61850, which is more for substation, looking at the feeder and switches and all those communication there, the substation distribution feeder level. 1547 is more cybersecurities, and this gateway connected to this one collections of group one, which is microgrids, right? Battery, EMS, and then we have so-called federated learning. Federated learning is all about trying to digest all these the heterogeneous data coming from this, but I don't want to share raw data, but rather can be able to only share what I need to share, maybe in terms of model weights, but it could be some other form too. It doesn't have to be always in terms of weights. So, and then it connects to the next way, input fold and then market. So this is a very, very important. One of the things that I'm trying to do is to build a test bed that able to mimic and simulate this architecture. And we are not there yet. I'm only right now starting to finish this partially we have built it, and we want to connect to external universities, the national lab, and connecting to their assets and so forth. And which is also my other purpose that I'm reaching out to different players. And we have connected a number of universities. There are here for RT test bed in the US. And but we still need, because I don't have all the leverage. IISc has other asset resources to have, and you may have the resources. We need to make sure that we can be able to talk to each other. But we need to solve the complex DERMS research problems. Okay, and so this is something that, and then when you look at cybersecurity, what are those threat vectors look like across these levels, and so if you see that lower level, most of the lower level one, you're going to see a lot of firmware attacks, false data injection attack, integrity attack, malicious updates, those type of attacks can happen level 1 and level 2. The more you go up in layer, level 3 to level 5, it's all networks, collections of networks, right? So you're going to see more denial of service, the distributed denial of service attacks, or it could be Trojans, right? And so, and ransomware. Ransomware is getting a lot of attention. Those are the things that you're going to be prepared to see whether it is just a very high level mapping. It's not a set in stone thing, but this is to be aware of the threats across the lab, across this. When we look at communication patterns in terms, it can happen any of these 5 ways. The first wave is actually centralized. Okay, you have a global authority that all these nodes, all these DER nodes trust. They send their data to them, and then they do the aggregation at a global level. It's as simple as it is. Okay. And single point of communication, but if failure happens in your node, then there is an issue. There is a problem with centralized in some ways. Decentralized, where you have some autonomy over each of these individual nodes, they can make their own decisions. Maybe it is as a wind turbine, it does its own thing, so it has its own load forecast or voltage regulations. And so decentralized is also something that is needed. And distributed, where they share their information, mutually agree upon some consensus and trying to make decisions that is actually meaningful for the global good in terms of the global network. That is not distributed. And if you really want to look at the emerging concept of locally federated and globally federated or centrally federated, locally federated is actually some nodes trust only some nodes. Not every node trusts every other node. So, and if you have that type of logic, and some of them has to do with the weights are shared and aggregated locally through mutual consent for those neighborhood nodes or handful of nodes, but there's no single authority to issue any model updates. Okay, so there is still some kind of, it's a combination of this so-called distributed thing, but still it's not every node is participating in the trust process. Okay, and this is another emerging concept that's also that may happen in all those architectures, depending on which level you're talking about. Centrally federated, global policy enforcement, exactly centralized, but we try to do the policy enforcement in the global side, but the application of weights happening through centralized dispatch of model updates. Okay, so there's a single source of the global authority that gives you this model updates to each of these DER nodes. So any of these architecture patterns can happen in any of these levels, but to give you an example, for example, for centralized, we thought as much. We didn't do dispatches reactive power to 10,000 rooftop PVs. So there's one single all layer all control centralized at one utility center. Okay, and single point failure is power central, right? And if you look at decentralized, decentralized example, like I mentioned, in each wind turbine floaters out of the basement. It's a very local, particular to one particular legal unit, trying to find very quick, fast local response to get the result of it needed. They would serve as something that moving. And then distributed. PV farms for any provide low congestions. That's an example for a distributed type of peer-to-peer kind of communication. And then in combination of locally federated, we have a combination of PVs and S reports to one as one unit, as one single entity through the utility. So we have DER to reader utility. And similarly, we have collections of EV fleets, aggregates manage EV fleets and report to details, but essentially, this is just one example to show you, how one can envision these architectures to different use cases. Okay. And we try to map these to different levels, and if you where these architecture may fit, the more the bottom layer, you're going to see more distributed locally federated. The more up you go in level 5, you're going to see some hybrid architectures that you're going to see. There is no set and straightforward answer. There's no one size fits all. There's a combination of this architecture needs to be tried out to figure out really to see whether which one gives you the trade-off that you want. If you want cost versus latency versus whatever the response that you're looking at in terms of response time. One of the things that I keep on hearing when I talk to DERMS vendors or ADMS vendors, there's different opinion. For example, if you look at the bottom 3 points, one vendor says, "Oh, our DERMS solution operates independently. Bundling with ADMS limits our flexibility, forces lock in with big vendors, focuses modular, decoupled deployments. They don't want to, their view is DERMS is an independent solution." Okay. Whereas the other one, if you talk about, we already use an ADMS for load management. Why would we bring DERMS? It's another new system. It's going to confuse. Okay. So there's another perspective of users. And then third one, DERMS should be tightly coupled with ADMS to streamline data. More like an IT managers or looking at IT guys, they really like this other system, want to separate OT and IT. They really favor, this separation of ADMS and DERMS. Okay. And but they're stuck because operation wants control and no clarity on consistency on API and data models. So there are different views of this technology across who you speak with. But one thing is certain, because you have more and more dealers, you have more bidirectional flow. It's going to be more threat vectors. So you need to figure out the separation of layers really to address these threats. And there is a confusion in terms of number of overlapping functionalities. Okay, in terms of the same DMS and ADMS does the same lot of forecasting, which DERMS can also do, right? And what is that fine line of borderline that separates the distinction between this functionalities? And there's no standardized interfaces, control protocols, and everything is vague. Architectural ambiguity, like I said, this one example I showed you was just to what are the forms of communications made possible, but there's no clear guidance which one of these architectures can work well in which level. And depending on the size of the utilities, depending on the size of the network, it may vary, and right. And not every big utility that talk to them are favor of cloud. They don't want cloud. They want everything to be a dedicated thing. I don't know about in here, but I think, perspective, it's not in favor, of conservative utility mindset. And so these are some challenges that you need to be aware of, and how do you separate these two jobs? Or does DERMS solution rely on ADMS or? And I have many interactions with these companies like Schneider Electric, Surveillant, and you name it. They have their own perspective of what they think DERMS is, which is completely different from one company versus the other company. So, and so we need a test bed to really want to test all this realistic multi-device testing with real standards. There's the conflicting controls. Of course, there's a lot of data these are going to generate, so AI can play a role there to do a number of things. At the same time, you have to be mindful of risk associated with AI as well, which I will also talk about. And on the right, you could see different types of tools and software that these companies have for DERMS. So if you're a PhD student listening to this conversation, what is the dissertation title that you may want to work on? There are a number of titles. How do you scale these communications? How do you accommodate more of these heterogeneous teams? Okay, you gotta have the standard, so-called what we have right now as a guiding document to do so, but that doesn't give a big picture of everything what you need to know. Okay, and of course, there's lots of work on anomaly detection. There's so many papers on anomaly detection AI thing, but still, is it really practical? What happens if the model is poisoned or data is poisoned? How do you address this streaming data? And so there is challenges in addressing that as well. We talked about interoperability across vendors, protocols, legacy. It's a real challenge. I don't know whether we can find a solution right now, but it's going to take for another new standard, more discussions, more working body to get together to really decide about what is feasible, what we think, and if we can able to come up with an agreement there, right? And resilience. Everything we do to make sure to stabilize the grid. Okay, there's uncertainties that is happening due to physical, also due to cyber. Not only on cyber, there is also real aging infrastructure, right? How do we define this resilience? Resilience can be defined in both physical angle, also from cyber's perspective, right? So there's a big piece there, and how do you store them? And how do you have this observability to make sure that you have a good scoring scheme, that is actually comprehensive? So there is that purpose there as well. Of course, we have optimization as well, that cost. If you talk to a company, they only care about cost. How do you optimize these services at the lowest cost or at the highest cost, right? To make sure that it's profitable at the same time, and to make sure they are seamless interoperability, rules, economic such. Privacy and policy implications are a big thing, of course. Data is sensitive, and utilities, they're very hard to get into the data. So it's as if you're a researcher to working with companies, but and you are working on synthetic data or simulation data, but how do we understand those real life, realistic scenarios? How do we get those realistic rare events? We don't have rare events. If you look at all the training data, all the AI models that you see, they have all these data set, but none of them are realistic. Some of them is not even. And there's not in the training data or class labels, there's not a rare events, that is has collectively that you can use. You have this, you have to augment the data to make sure what you think your test data may see to look at your, whether you're looking at F1 score or overfitting, So this, to have a good data set that has a collections of rare events, the rare signatures that happen, because rare events do cost catastrophic consequences. It's not those small, powerful, this fluctuation that it still has an impact on power quality and other things. But how do you make sure this nationwide threat doesn't hamper or protect the infrastructure what we have laid out? So it is very important to look at. This is just a slide that talks about these three key different protocols. 2030.5 is more level 2, level 3, 4, 5 more focused on substation, responsible for the pricing, metering, demand response as well. And 2030.5, 61815 is level 1 and 2, more at the lower level, remote access to field devices. 1547 is talking about what is this minimal compliance that you need to have for cybersecurity. So dealing with Modbus and MMS level 1 and 2. So you have to be mindful and understand these protocols document if you really want to, get to know more about cybersecurity. Like if you really want to do some vulnerability framework, I heard somebody wants to work on vulnerability framework. What does that mean for each of these communication protocol? And so you probably need to look at that. And there are so many standards to look at this. There are 3 different layers. Again, this is from a standard body. You have, or you're looking at technical side, or you have this 1547.3, all these things. But if you are you looking at organizational cybersecurity or the business requirements cybersecurity, there's different standards there. Okay, and we're only talking about the technical side. There is organizational cybersecurity. There's also a business perspectives, which we're not even looking at. That. What are the implications of that? And so I don't even know. I mean, there's so much of work that we need to really understand the full cybersecurity landscape. When we talk about cybersecurity, you probably heard about all these CIA principles, right? Confidential, integrity, and availability that's surrounding the data, right? Now that the new one is also added accountability. Okay. So what does the CIA property means in terms of DERMS, right? And it means confidential is preventing unauthorized access to whatever the systems that you have in terms of whether it's looking at custom managed use of data or to make sure that that doesn't happen. Integrity, false data injection attack, or tampering, or to make sure what I'm looking at is actually coming from that sensor, or is it actually manipulated, or is it actually, we don't know, right? So grid frequency, voltage, DE, or output data are not altered or corrupted. Okay, so integrity is also it's key. Availability. Okay, we want to make sure all system operational and functional. Okay, even during those uncertain events, whether it's and natural calamities, whether flood or wildfire or whatever that is going to hamper these critical infrastructure, still need to make these systems operations. And availability is key. And how do you isolate these subsystems and still provide reliable power? Accountability, logging every user asset, data, gateways, applications, and so forth. How do you make sure that you have all these traces, that is visibility, so that you can know who's accountable for this? So, right, and zero trust helps in some of these as well in terms of accountability. U.S. Department of Energy has looked into this DER thing, and they come to these three big categories of threats in terms of DER. One is actually aggregation risk, another one is the malicious DER configuration, another one is the manipulation of communication data. If you look at aggregation, during all these hundreds of nodes or thousands of nodes trying to send these signals and these aggregations, trying to aggregate, whether it's an EV or solar or whatever that is, what can happen? Based on our finding on the papers, what we see, you can see the ransomware and trojans are likely to occur, okay? And in those in this particular scenario, right? Because aggregator is trying to aggregate, they may lose this confidentiality and availability. So an account. So if you only look at the ransomware and trojan, all three principles are compromised. And stride mapping, tells you what that means in Microsoft. Stride mapping, S means spoofing, T is tampering. So according to this, is actually I is affected more, which is the information disclosure, and D, which is your denial of service. And so this is just another high-level mapping. Similarly, for when you look at malicious DER configuration, when new SCADA device, new sensor, new RTU, comes into utility, and the DER configuration can be exploited by multiple ways, by production during installation, or during computing, or during patching scenario, or during file update process. So there are a lot of devices, all these things have default passwords. So and how do you make sure that these configurations are supposed to be done by the people who are supposed to be doing it, and right, and so this is another way that malicious DER configuration can occur. Manipulations of communication data, right, and through malware attack or large spoofing is one way that this can be done. Again, in this case, you could see that false data injection or legacy systems or poorly secure devices, there is not a lot of encryption, is going to be effective and integrity compromise. One way to show example of this is through man-in-the-middle attack scenario, right? There's always somebody there listening to you. It could be insider threat or it could be an external actor, listening to your conversation with networks and users, and they may deploy, any type of means. For example, ARC spoofing. In this particular scenario, there is an inverter trying to connect an aggregator. Hey, I want to talk to 1.20. Okay, and is waiting for an ARP reply. It did reply, but all of a sudden there is new device C is trying to send a flooded ARP request. Okay, and during this flooded ARP request, the ARP table could be updated. When you have the ARP table updated, Now, during this, now we've got a things devices and aggregated. Aggregated things, devices, and inverter. Then we have a wrong direction of communication flow happening, right? And you want to avoid such scenarios. So if you're looking at this, we have done a lot of attack scripts that is available on GitHub, as part of our DOE-funded project, which we will release. It's actually private right now. These attack scripts can be actually used for whatever that you want to connect in your own world, right? I think in your own simulation. So replay attack, you have denial of service, you have part spoofing as well. Another big picture of looking at this DERMS in terms of resiliency is separating them into 3 layers: sensing, communication, and controls. This is another view of what I'm already talking about. If you look at sensing layer, the lower level, right? I think you could see malicious configurations, software vulnerabilities, backdoors, open source. Open source intelligence is another key thing. A lot of substations, there are a lot of devices whose IP address, whose location information can be known by doing this open source intelligence and may compromise, and so this is another serious thing. And the right side is what are the current existing mitigation approaches that people commonly use to avoid that, and so if you're a PhD student or a postdoc looking at this, okay, how can I harden these threats much more different way, or maybe are the new techniques available to attack these attack vectors, right? And similarly, the communication levels, we have open ports, uninterrupted communications, remote access, and all of this. Right side, you could see access control mechanisms, and cryptography and integrity check, right? This is just another perspective of how to look at threats and available mitigations. So you could think about some new ways to solve these threats across these layers too. And cyber resiliency is defined as the ability to anticipate, withstand, recover, and adapt to adverse conditions, right? Not only that, but also to recover to a trusted state. Okay, how do you know it is a trusted state after the destruction of the cyber? Right? How do you evaluate? How do you make sure that state that you're going from and going to is trustable? There's a lot of research in that domain as well. The definition may look simple, but it's a hard problem. And zero trust is getting attention, right? I think all it means is don't trust anybody, users, devices, access, gateways, and applications, and you want to verify every single thing. Gone those days where these old technique of perimeter-based defenses that happens in the firewall, right? Now everybody is looking at, okay, how do we do this? Zero trust means it could be with blockchain. Zero trust means with post-quantum cryptography, or zero trust means with simple managing the policies with identity access management. If we have separation of the least privilege access control, so if we can able to do that, then at least you have multiple layers to really to address this particular thing, right? It's just a concept called zero trust, but you really need to have this multiple layer of defense to make sure that you have isolation can be done so that your system is operational under those difficult circumstances. And policy generation, right? There is a lot of work people are doing using the reinforcement learning on generating these policies, across these levels. So one may look at that as well. When we look at cybersecurity in the big picture, we have to understand the difference between the vulnerability, attack, and threat, right? This is just a slide that I tell everybody to make sure that, okay, you have SQL injections. If you go to a website, you have username and password. If you type one for username, one for password, it logs in and give you access. Then you didn't do a data sanity check in terms of the database. It's a very legacy system, still have it, whether it's looking at your sensor or thing. So then you're exploiting ransomwares and penetrating this, So this is something that you might avoid. And cross-scripting attack, where session cookies should be protected. If cookies are not protected, then you're going to have stealing of your sensitive information through cross attack. Okay. Buffer overflow attack, which is, as the name says, the memory, right? If you overwrite, if you try to make sure that your buffer is not finite, then you're going to see attackers trying to put those excessive input to execute a code for a nation state threat, right? There are hundreds of people sitting trying to exploit your system. Okay, and we cannot defend against them. You have to make sure that it's patched. You have to make sure that you have, what is the vulnerability? What does the vulnerability look like in your thing? That brings you to zero-day attack. right? And which means it's a previously unknown security flaw in software, firmware, and hardware that is discovered by attackers before the vendor became the right? That's what it means. So we have only 0 days to fix it. Okay, so unless CVE comes up before an attacker does, or maybe you have or attack has happened and you have then you became aware and do a patch, right? So it's something that it's going to be common because you have so much of dependency, so much of connection, so many software, so many tools. And examples of real-world 0-day attacks are some of these examples, right? People have carried overflow attack. People have used Siemens attack on Siemens telecontrol server. Their SCADA systems, firmware vulnerabilities and Enphase IQ solar gateway. So these are real CVEs, and the left-hand side shows you how the attacker identifies through a VPN version exposure to internet, then it gets into remote access to gain access to DERMS backend, silently installs malware, get list unauthorized control commands to inverters, make the grid unstable. Okay, and so no patch, no defense. So you have to make sure that you know how to address this. Speaking of AI and machine learning, AI is data. We all want data-driven solutions. It's good, but what is the risk associated with this machine learning business? Many things can happen. Okay, and model evasion, which is basically perturbation of the inference stage to correct model predictions. Can models be hijacked in terms of you're thinking you spend so much of days and time to train that particular thing to have a good model thing. And if model can be taken away, then your model predictions could be wrong. Data poisoning, right? And which is as you modify inputs. How do you make sure your inputs are coming from your real thing? How if you do see some other users, other ways inputs are being compromised, how do you quarantine? So data poisoning can also another ways to model inversion, right? Your hyperparameter weights can be stored, right? Or it can be returned with the different things. So the side channel or software-defined based attacks. So model inversion is another way. And membership influence. You may have access to your knowingly trying to get a user behavior, device behavior, asset behavior about something without even their permission. So you're violating their privacy, right? And how do you make sure that you create an environment that you know that you don't violate that? But all of these are real things. Okay, it is not. It's easy to say, but it's very difficult for anybody who wants to work on machine learning. Then you need to be aware of addressing these things, how your system doesn't compromise all these 4 aspects.
Privacy can be violated even with federated learning.
Yes, and there are many ways. I think right. So and when we did that, we have one of these tested out there for ADMS symptoms. So we found some of them, and each has own labs. PNN has the labs that people are using for distribution. We have testbed. You have Cybersecurity now. So it has some co-simulations. You have some simulation. Mostly it's all simulator. They have their own small pool of devices connected to their lab setting, and they call it as a ADMS of distribution. It's not still to a scale that we really want to simulate DERMS related challenges, right? When speaking of DERMS, when we already talked about all these challenges before, right? I don't want to repeat this again and again, but my question is, this is where that we are trying to get into to see how can we get to this test bed, So I will put this link or send out the link to users who registered. Maybe if you have test beds, then I would like to know what test bed you have, so we can able to get to know more about your test bed. And this is something that we want to release a white paper sometime next spring to make sure what we find out on the test beds. At UNB, we have a collections of some just devices, AGX and Nano devices. These are high-end GPUs. The AGX one cost about $2,500. We have 15 of them or so, and we have some Nanos, which also have cost about $500. It can also do some GPU intensive calculations, and we have Raspberry Pi. the rack that you see over there is something we built, and my team, Akshay and Harish, and the full-time research team spent 2 years in actually building this. And we have collections of firewall. We have an on-premise cloud, as well as we have AWS infrastructure. We are working with our national lab to build this anomaly detection, intrusion detection for this solar project that we have in the solar inverter project. So we have a number of these GPU devices. We have attack scripts, and we have machine learning, deep learning, running to catch these attacks. Okay, and we just did a 3-day boot camp just a few weeks ago, and we had 18 students participated in many universities, and they had a good time in getting to know about how to install NVIDIA, how to configure NVIDIA devices on edge, how to run predictive learning, say attack scripts. So I think this is something that I'll continue to promote and provide dissemination through next cohort of the boot camp as well. Okay, and moving further on autoencoder use case, you probably heard about autoencoders, right? I think basically autoencoder has an encoder and decoder, right? It compresses the input, and then you have this. It relies on these 3 different waves, WBA weights. You have biases and activation functions, depending on which activation functions you use. It's the bottleneck layer is something that you want to minimize the number of layers, optimize. You want to learn from your presentation from the input sequence, and trying to see whether you can be able to reconstruct your original signal at the decoder level to make sure that you can catch that anomaly, right? And there are many variations of autoencoders. There's the sparse, there's a basic, convolutional, depending on whether you're dealing with image data, text data, and what is the use case there. So it's interesting to look at, and for fault identification, and in general even for data interpretation, dimensional reduction, state estimation, and forecasting. This has been actually used, right? One of the quick example is one of my students generated a denial of service traffic attack using the testbed that we have, and he pulled up all these parameters, features, bytes per second, packets per second, TCP flags, protocols, and other metadata, and deployed a couple of autoencoder models. And before he deploys, he was trying to simulate the slow traffic or fast traffic, or random traffic in terms of understanding the traffic behavior, and trying to see how this autoencoder really performed. And clearly, it's very clear from this. He used some membership functions, mathematical functions, to model this slow and medium and fast evolving traffic. So it's very clear that for slow and random, the autoencoder is clearly can distinguish between what is normal, what is abnormal, because there's a distinction already there. There's not much learning there. Whereas in terms of the pulse signal, where the anomaly is inherently embedded into the input sequence, it's kind of difficult to distinguish that. So this is what the finding that he used. And also on the right side graph, what you see here is what he learned is only certain neurons are activated time and again. The same neurons activated again and again if it sees the same pattern. Okay, so depending on distinguished patterns that you will have in your test data, you can train your autoencoder to make sure which neurons are activated and which neurons will actually function in terms of understanding the learning behavior of that particular pattern. Going further to federated learning concept, right? I think federated learning has gained attention because, you don't send, you want to preserve privacy, right? And you want to make sure that you send only model updates to do the sharing, right? And one of the things that one has to really understand whether federated learning makes sense for my use case or not. Okay, especially in power systems, when you have multiple DER types, EVs, solar, battery, wind, these are heterogeneous data set. You have non-IID type of data set. So federated learning makes sense for a larger group of networks which are heterogeneous in sense, where you prefer some sensitivity. Okay, and also you should have the infrastructure to do so. If you don't have the infrastructure, it doesn't make any sense. It costs money to have that, edge devices to be hosted, and the cloud, and the latency calculations. And if you really, when we talk about this edge, right? One of the standard talks about is everything should be 1 millisecond. At 1 second, you should have all these anomalies to be detected. How is it possible when you have so much of DER's penetrations happening? Without edge, it cannot happen. So edge is actually needs to be part of the process. Okay, and when you look at federated learning, there are a number of federated algorithms are available. Fed average, starting from fed average to all the other things. People only, you see papers mostly fed average. I don't see papers in other types of federated algorithms. What does this mean? How do I select these different algorithms? To give you an example, for example, if you use fed average, to do average of all the participating clients, okay, what is happening is fed average doesn't distinguish between a slow streaming client versus a fast streaming client. It has it treats everybody as equal. Okay, so there's a bias inherently present in it. It is not suitable for non-IID type of thing. Whereas if you look at the other ones, where we have FedProx and FedNova, for FedNova, right, they're not lightweight, but they're still heavier, but they are better for non-IID. They have fairness. They sometimes fairness is. What does fairness mean? Is it something important for your research, for your use case? Then you use it. So you have to really to look at to see whether you want lightweight, do you want fairness, or do you want just simple average across multiple nodes participation. So you have to select according to these federated algorithms and so forth. Mostly this. And also the update frequency, substations, the frequency of the streaming would be high. Rooftops PV update rates would be low. So how are your update rates? So you need to also look at that update rates as well. And here's a little number of work on federated learning algorithms, what people have used and some way they evaluate. And so there's another way to look at what people have done. But this is a new evolving, emerging concept. My team has done some simple federated learning environment with just 2 clients. It's still not a robust thing, but something to get to know what is this federated learning? How do I model this thing? And so in this particular thing, my student has taken 3 signatures. We had an inverter data that we received from A&M, a real inverter data, and then we actually injected some different types of function, pulse, Gaussian, pulse, and sigmoid of different varying durations. Somebody's speaking. I'm not sure. So, in this I was hearing something. So version 1 is a continuous 3 hours of injection of that. Version 2 is 3 random 1-hour windows. Version 3 was a mixed 5-minute signal, 30-minute continuous, and 18-minute signal. And we want to figure out to see whether, can be able to do averaging and can be able to do some kind of learning from this. Okay, so what we found out is, it takes with even though it's only 2 clients, and the MAPE savings was better, in terms of it's still marginal, but still comparably training MAPE was better to reconstruct or find an anomaly, and I think we used LSTM for the particular purpose, and you could see that all of these signatures and how they performed, and it looks like the recall rate for version 3 was lower. Higher recall is better, right? And so version 2 was 0.59. Version 1 was even low. For some reason, you couldn't find a lot of anomalies from version 1, version 2. Version 3, you were able to do better. And one of the things that he also did, my student Kareem, and he's a PhD student, is, what happens these edge devices? If we continue to stress these edge devices, either through mimicking the denial of service, or maybe there is inherently too much computation going on in these edge devices, then how do you actually capture the anomalies that the edge is actually experiencing some kind of anomalies, in terms of the memory or GPU usage? Similar work he has done in terms of capturing some signals and train them, and then you find by LSTM actually perform better, even if it takes longer duration. Okay, and so that's something that he has done. I'm going to skip all these similar results. One other thing that you also need to know is dropout layers. So you can change, even if you want to work on these machine learning, you can do this varying rate of 10 to 30% dropout rate to see whether if you leave, dropout means you're dropping some certain neurons, to make sure your use case still function to achieve the same accuracy or same trade-off that you wanted, right? 10% neurons, 30% neuron regularization, right? So, and in this case, it doesn't make any difference, dropout. And my other PhD student tried with why LSTM is so suitable for edge. She had tried 37 varieties of LSTM models, and trying to figure out to see, using this hyperparameter sweep and across to see, from 50 to 100 sequence length and looking at ROC and AUC curve. There are only certain connections of models. These blue dots are each one of them is an LSTM model. There are 37 models in this thing. Okay, and there are only certain models perform better, not everybody. If you look at the right side thing, there's only one model that captures more anomalies than the other 36 models. So if you're building a use case where the catching number of anomalies is important, then you need to choose that particular model. So here's another picture here where you see 10 different LSTM variation models is good enough to capture most of the anomalies in this particular thing. How do we do in the time? How much time do we have?
2 minutes.
That's it? Okay, so I think I'm going to quickly go to similar. We did some false data injection attacks. Again, the different methods that we use for that. And again, inverter data, and to show that, even imbalances present in the data, we can able to capture the false data. And looking at high machine learning models with the same inverter data, we have two stages of models. One, we fed to random forest. We forecasted the frequency information for future frequency steps of the grid. And then we calculate, once you do calculate, there is a residuals. If the residuals still hold inherently time series component, stationarity checks, and you feed the residuals to another model, KNN, and you add residuals to the forecast for the original frequency and compute that. So we did this thing and treat that as a anomaly detection approaches, in terms of streaming data. It also worked in terms of, it gives you, it catches, there are 1,400 anomalies, it captures almost thousands of them. Still, it can do a better job, but it did a good job in terms of. One of my other students was also working on LLM workflows on DO data to see how we can create LLMs for across different cloud framework and look at the cost queries for different APIs. So this was recent work was published in IEEE Cloud Summit, and and this is all about running the containers effectively. And she found that even in that particular generate some CVEs, Google Cloud performed better in terms of the anomaly detection in terms of the cost. So Google Cloud is the all these models has to run on some cloud, and it has a cost associated. So it's, from the cost perspective, which cloud is actually performing better is the overall goal for this. I'll take another 2 minutes here, and we have a new award on substation. There are a lot of attacks happening, gunshots happening in physical substation tampering. So, we are asked to deploy to detect, machine learning models to detect malicious versus non-malicious gunshots that are happening in substations. It is a real threat in the US, and it can happen due to terrorism, vandalism, blah, 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 whatever you can see here, a wide variety of reasons. And when we talk about cybersecurity from substation protocol, there's so many protocols you could see. There's one number of different types are available. This is another area folks can focus on substations as well. And so we have this project. We have a collection of radar, seismic sensors. We have UAS. We have camera systems. So we are fusing all these data to catch the intruder and trying to work with law enforcement to send those signals as well to make sure that we can track them. Okay, this is another interesting thing. I'm not going to go over the VPP side. We have done some work on that. We've done some transformer neural networks applications on this. Recently we formed NSF funded a new infrastructure security in the FAI for the 3 universities that are partnering. George Mason, UND, and University of Arkansas. It's for all for critical infrastructure. Only one center in the US is funded for critical infrastructure. It is our center that's funded for this. Okay, and we just recently met with 60 companies in Fayetteville, Arkansas to make sure that these companies invest in research. problems of interest to them. The annual membership fee can range from anywhere from $50,000 or more to become a member for the center. And so we have a number of companies interested to participate and have agreed to be part of this. So we're excited for this initiative that we have. And so we have some, the structure for this is the money goes to common pool, and depending on, it's voted by the industry advisory board, and depending on, who is selected, and make sure that the project is executed and so forth. Right. With this, I know I went a little faster, I could have gone slower, but I know that in the interest of time, I thank my sponsors, DOE, NSF, and EPSCOR, and IEEE local sections, and Red River Valley section for this time that you get. I'm open for questions, what you have.
Audience, any questions? Then after that, we'll come.
Sure. Do you have any questions, folks who are listening online? Can you post your question? You should see here, right? Chat. So the membership you're asking about, what is C_M of F, right? That is related to that machine learning exploitation, that model data poisoning, right? And you have to have some distribution function to really to triage those, whether it's due to model poisoning or data poisoning. So it is just a general function. So I would encourage you to read that paper, what we have, and then maybe you have some light. It could be any type of distribution function that you want to triage these. Okay, when you see this data poisoning or model poisoning or model inversion, how do you triage them? So you need to have some way to look at the probability score. You have to look at some way of to triage them. So that's just a general functional statement, but it can come from any type of mathematical functions. Next, good question. Oh, we can see the screen? Yeah, good question. Yeah, good question. So ADMS is connected to that substation, that 11 switches, all those distribution management system, right? It's a little different from, DERMS, but still, DERMS is all about dispatching. It's all about this forecasting and the flexible services that it can offer. But ADMS is on the infrastructure connected to the grid itself. So that's why I said there's overlapping functionalities what this ADMS and DERMS is, right? And DERMS, you can think about this. It provides all these flexible services, for all these DER types. Whereas you need that infrastructure in place, the substation switches, relays, all those things still connect to the grid to turn on, turn off, and so that is handled by this ADMS platform. Okay. You guys can see this. Why you can see the chat thing? Let me see. Maybe I should open the. Oh, you made it out. Okay.
Could you share how federated learning supports cyber resilience?
Yeah, interesting question, right? Federated learning supports cyber. Federated learning, okay. So if you are going to preserve privacy by not sharing local raw data, right? Only sharing model weights. So your raw data is withholded, right? Which means you have some privacy. So which means you're not, in some way, the way I think cyber resilience is related to this, you're not able to share your actual sensitive DER or user data that may be exploited, right? In this particular context, is it one way? But like Dr. Gurunath mentioned, if there's anything is possible, even in federated learning, you got to make sure that what is the right use case that you are deploying this federated learning, at what level, and if depending on those average functions you talked about, you have fairness, you have what functions you will deploy. There is exploitations may occur depending on how you see that. So I think cyber resilience is it is a general word, resilience, right? I think we argue, we try to see whether we can minimize this attack vector through this federated structure, right? And so I don't know whether I answered that question or not, but I think it's something that preserve privacy. You minimize the attack vector threat surface, then you have some level of resilience built into this. That's a simple way to say it, but yeah. Huh?
Yeah.
You can ask me any questions you want.
So, ransomware is also one type of malware, right? So
Yes.
can you tell what is the typical behavior of ransomware, which is not seen in other types of malwares? Are all the malwares behave similarly, or there is some different behavior?
As the word says, ransom, right? If your system is compromised and will be released at the cost that you provide at a ransom, right? So this is something. Ransomware is financial thing. It is trying to exploit your financial thing. There is the big difference to make sure that the attacker is trying to get for his goal to get that money, and to make sure until you provide that, he's not going to give access to the thing, right? So that is
Propagation point of view. The way this program propagates through the network. Are they similar to it?
Yes. Like any other malwares, the propagation is still similar, but to what extent they can penetrate to, whether it individual asset or users and compromise, and then, so then the propagation is still similar. Yes.
Do they add the same portion of your hardware, or it differs from malware?
Like I said, it can occur from level 3 to level 5, right? In border and network level, any of those level 3 to level 5, ransomware is possible. And where there is a network, and where is the systems where you have those patchy software, the legacy systems that these folks trying to exploit, and it is possible. It is another form of it's a very good question. I think as far as I know, the propagation is any like malware at a cost. Maybe there is that's worthwhile to attack that particular system. That is, if that compromise, the attack consequence is very big to disrupt the entire process, right? So ransomware likelihood is going to attack those nodes, which is going to affect that operational aspect, to create that instability. Whereas malware, other form of malware, they may not cause instability. They may still provide some disruption, but it may be minimal, right? So the distinction of selecting that particular node, which is actually going to cause a catastrophic thing, it could be a distinct signature of how these people are selecting these nodes. Just it's a good question, but I think to me, I treat it as another form of malware. I think that's all it is, but financial gain. Did that answer your question? Okay.
Federated learning, last year we worked with Accenture, basically load forecasting. So you have this US database for the loads from different buildings. I think forgot the exact database name. We applied the federated learning. We actually have a hardware test beds in CDS. So on all our Raspberry Pi.
On Raspberry Pi.
On Raspberry Pi. So what we found is that if you actually take care of the pre-processing well and try to remove all these outliers, Fed average is much better than the Fed prox, is what we found compared to other algorithms. We tried almost 4 different Fed algorithms.
Sure.
With respect to the load forecasting, we found that Fed average turns out to be better.
Yeah, I mean, again, depends on the data set and the use case that you have. That's an interesting observation. I'm curious to read that paper to see.
Or just accept it. I think there will be some possibly clouds. I don't know.
And you're right. The more and more we do pre-processing at the local level, trying to do that, I think the performance that you're going to see is going to be outsmart.
Because at the end of the day, procs and all these things, the improvement you see is very marginal with respect to the computations that you need to put on top of it. Petra is very simple and
How many clients you tried? If you have any
30 clients.
30 clients.
Hardware.
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 Okay. And it's Raspberry. Raspberry can handle that much of effort? And as you scale, look at hundreds of nodes and thousands of
It's
nodes.
it's the top version of this thing there.
Yeah.
It works.
Yeah. So yeah, I think there is a lot of learning in, there is no one size thing. I just want to show that so many of them, but I see a lot of papers only on Fed applications. There's not people are using more use cases for other federal. So there are many.
We tried.
I myself is curious to see what is this differences. I want to know what is this difference that I can able
Four
to
different kinds of. I think we have finally we found that the increment that you see is not that.
Yeah. Good.
So, more questions? Saraswati?
Hopefully, I gave some useful time for your time to give you what we are doing. And I think thank you for being here and let's say, and see what nice work that you guys do here. So